The today lecture is about GPGPU as a service. This is an advanced topic in the field of cloud computing because one of the most attractive today use of cloud computing is offloading part of the computation on the accelerated node. Uh, this is done mostly from HPC and for deep learning applications, but above all, even will be done in the mobile application with the advent of edge computing. This is the outline of the presentation. Will be an introduction about GPU as a service. Then I will show you the architecture of GVirtus, GPGPU virtualization service. The split driver model is a model we already had some information about it when we talked about containerization and the difference between virtual machines and container. Of course, when a new layer is introduced between two already existing layers, there will be a lack of performance. So we have to check and benchmark what happens if I offload some part of the computation from the local machine to an accelerated machine. And this is a little surprise because while the uh, cloud computing topics are usually related to big computation, the most part of the cloud computing services are related to mobile computing, and even mobile cloud computing is a good percent of the cloud computing application. And, for this reason, we will talk about the Android integration of GPGPU offloading, and then, of course, the conclusions. First of all, why GPU computing? Actually, all devices we are currently using are provided by GPU. GPU are made mainly for graphic units. That's because graphic processing units is a kind of a coprocessor. The idea is not new. If you remember the Commodore Amiga, the computer of the 80s. It was one of the most common example of a graphic coprocessor. So the idea is not new, as I told, is mainly devoted to real-time graphics for video games and so on. The most part of the computation is the same algorithm applied in parallel, massively parallel to a huge amount of data. If you are thinking about texture that have to be wrapped on a 3D model and real-time calculating the lighting, reflections, whatever, yes, this is the typical application of a GPU. But here we are not talking about the GPU used for graphics, but we are talking about GPU for computation. The idea was at the beginning of the 2000s, the development of high-performance GPUs was one of the most in the most intense time of development, and basically NVIDIA was devoted to really high-performance graphic processing units for video games. But the idea for scientists and engineers was why we have just to apply algorithms to do real-time graphics if we can use exactly the same hardware architecture to perform high-performance computing. And of course, the today panorama of GPU computing is populated by mainly two kind of devices devoted to gaming, definitely really high performance in graphic production, and this kind of device could be used professionally, even for graphic modeling, 3D modeling, and whatever. And on the other side, the GPU computing is dedicated for pure computation, because if you just change the algorithm instead of projecting um, textures and bitmaps on solids, you can solve, for example, complex systems of equation. So why GPU virtualization? First of all, because GPUs are expensive. GPUs for computation are really expensive. GPUs for gaming are expensive, but not as the GPU for computation. If you just imagine that at the time of speaking, GPU for gaming, for let's quote professional gaming, costs about 1,000 euros or 1,000 dollars. The counterpart for computation cost at least 15 or 16 times more. So buying GPUs for computation premise, of course, these have to be done during the infrastructure procurement, the procurement of a big computing of computing infrastructure for big data. It's not an easy way. Is especially for public administration, it's not easy, it's costly, and so if we buy GPUs for on-prem application, that means we have to spend money. We have an increase of the total cost of ownership and whatever. So for why GPU virtualization? I could have interest in GPU virtualization on my own machines, because in this case I can optimize infrastructure procurement. That means I have not to buy GPGPU for each student of a class, but I could just buy a bunch of GPUs, put these GPUs in a server, and then share these GPUs with the students. And in this way, I have to buy less GPUs than buy a single GPU for each student machine. In this case, of course, I minimize the total cost of ownership. If you imagine a computer lab where I have to teach GPU computing, or just I have to teach data science or deep learning or whatever, I should buy a GPU for each machine available in the lab. With GPU virtualization, I could just have some virtual machines or even remote machines accelerated by GPUs. With GPU virtualization, it is possible to enable machines that are not provided directly by GPGPU resources, able to run software that needs for GPUs. For example, again, minimizing the teaching costs or even time to market improvement, because I can raise a class of expert in GPU based machine learning applications without having real and costly GPU device. Of course, on cloud, there is a huge interest of GPU virtualization, even because on cloud it's possible to rent GPU resources, but really often is renting using the pass-through technique. The pass-through technique is not real, is not virtualization, is not multiplexing. Pass-through technique means just on a the cloud management software enables virtual machines to be connected directly to the real GPU available on the server where the virtual machine is run. While the interest of GPU virtualization in the cloud is different, the interest is multiplexing, basically having some GPUs that could be used with by more users, and that's of course improves the business. And of course, when you deal with the cloud infrastructure, having GPU utilization and multiplexing means save money on the cloud bill, because if we just move from testing the cloud, the public cloud, to use the public cloud, we discover that the bill is an important issue. This is the architecture of GPU virtualization, GPGPU virtualization. This is the architecture of GVirtus. Is a tool developed at University of Napoli Parthenope, the Department of Science and Technology, but is a common approach of virtualization, especially in containerized environment. Uh, Basically, everything works using the split driver approach. This will be detailed in the next slide. We have a backend and a front-end components. The backend is on the accelerator node. The front-end is on the virtualization node. And the front-end basically imitate the libraries used by the GPGPU applications, while the backend perform the actual computation. This way, the multiplexing is possible and could be even variable, and the overall performance are not so bad. It depends by the application. We saw some benchmark about this. In this slide, we can see two different kind of virtualization, or better, two different technologies are virtualized: the NVIDIA and AMD. Basically, the approach is exactly the same. The most important component in this is not the front end and the back end, but the communicator. Basically, the software component that perform the interaction between the front end and back end, because the main issue is communication and network connection, virtual network connection between the front end and back end. The last thing to be noticed in this slide that is remarkable, we can have both virtualization nodes and so virtual machines running on virtualization nodes that use the acceleration that offloads code on an acceleration node, but even remote machines that are actually physical machines, are not virtual machines, that could offload computation on the accelerator node. Of course, the connection between each one of these parts is critical, and definitely very critical. GVirtus works. That's almost the first thing to say, because it is virtualized GPU is not trivial. It's not an easy task. GPU is a software component for GPGPU virtualization. That means is not for visualization, but is for virtualization and remoting. Virtualization means using the same device on board the physical machine used by several virtual machines. Remoting means sharing a physical device with remote machines that could be virtual or physical as well. In particular, GVirtus is hypervisor independent. We can use GVirtus with different hypervisors, and is even a communicator independent, because in case we have different deployment scenarios, we can have, for example, the need to connect the backend and the front end using just the TCP/IP or InfiniBand, or the shared memory between the real machines, physical machines, and virtual machines. Of course, GVirtus is open source, and at the bottom of this slide is the GitHub where the software is available. And basically, GVirtuos is mostly used with uh, NVIDIA CUDA, even because it's the most used framework for GPU computing, but actually it's not limited to NVIDIA CUDA because it is based on a plugin architecture. That means it's possible to offload kernels and I mean software enabled for GPU for NVIDIA CUDA and OpenCI. Basically, the idea is on the front end, the APIs for CUDA and OpenCL are mocked, basically fake APIs that has exactly the same signature of the original one, but instead of interact directly with the driver, these APIs interact with the communicator, and then the communicator with the backend, and then finally the communicator, the backend with the actual driver. There is even a really simple programming model for Java and Android, but only for CUDA. It was not implemented ready for OpenCI, but it could be something in the future. It is the story about GVirtuos. GVirtuos was for the first time designed in 2009. It was included in a project proposal called Hope. This project was submitted to a local call for new technology project that was not found. Someone thought, okay, GPU virtualization, and in that time was even a cluster virtualization was useless. But never give up. And so in 2010 up to 2013, the GVirtuos project grew up as a research prototype. It was released in open source. During this time, the GVirtuos was in the radar of NEC, and they smelled the interesting approach of GVirtuos, and they contribute to the project, basically hiring one of the first developers. Then GVirtuos was founded by an European project, an H2020, from 2014 to 2017. It was a really good development of GVirtuos. At that time, GVirtuos was framed to CUDA 6.5 because one of the requirements was the stability, and was introduced the memory management. But the most important new thing was making it possible to offload CUDA kernels from Android device to high-end GPU devices. Finally, now GVirtuos is funded by a local project, is still under development, and basically the new interest is in use GVirtuos to offload machine learning tasks. And actually, there are some design, even there are some design topics, even for application to accelerators that are not GPUs, GPGPUs, but other kind of accelerators. As I told, the execute engine of GVirtuos is completely transparent because the libraries are fake, are basically the stub libraries. It is completely independent. It could be used by both physical machines and virtual machines. It is used by ARM and x86 machines, both 32 bits and 64 bits. The nice thing is you don't need to share the same technology on both front end and back end. You can have an ARM 64 bit mobile device offloading computing cores directly to an x86 64-bit uh, backend, and the virtualization, and in this case remoting, is completely transparent. You're not okay. You have just to execute the CUDA command and it works. And of course, this could be done basically in any configuration, because both front-end and back-end could be deployed locally in a public cloud or in a private cloud. And, any configuration of Mixabase is possible and was tested. As I told, it works on the split driver model. The split driver model is a key concept in the today cloud computing approach. Actually, the the main issue is I have two sides of computation. One side is called the front end side, is where the application runs, and the other side is called the backend, where the application have to offload part of the computation. If you are imagining, for example, in a container application for cloud computing, when you have, for example, a web server instance on the front end and an actual machine, a physical machine that have just to share libraries on the back end, basically what happens in Docker. Yes, this is exactly the right model. It works in this way. I have the application. The application invokes stub libraries. Let's say a library that perform the sum of two values. Just a typical example. The library is a system library. It should be executed by the machine where the application runs, but instead of execute a real library with a function summing two values, it is invoked another library with exactly the same signature, but instead interact with the backend using a communicator. The backend produce the actual computation, then the results are sent back to the front end. GVirtuals works exactly in the same way. The other interesting thing is where the components run. In GVirtuals, it's possible to have the front end in unprivileged domain, and it's interesting that the backend could be both in privileged domain in configuration where the main topic is share GPU computing with other virtual machines or remote machines, or even in unprivileged domain. For example, it's possible to install the GVirtuals backend on an Amazon virtual machine enabled using pass-through to use GPU devices, and then use a local machine that interact with the remote machine in order to consume GPU computing power. Basically, from the request point of view, I have the application, the wrap library, that is the stub library, the front-end driver, then the communicator, the back-end driver, the interface library, the device driver, and then finally the device. The GVirtuals backend must handle concurrent requests and have even to mediate between different threads on the same process on the remote machine, on different projects. This is easy, and it's definitely super easy to manage the connection with different backends, front ends at the same time. The point is the memory allocation, because let's say we have to allocate some memory, some part of the memory on the application, and the same memory have to be seen by the backend. The two contexts are completely different. Even because the backend could be on the same physical machine, or even on a machine on the other side of the world. This is exactly the same. Are two different memory contexts, and that means the memory addresses are completely inconsistent. Of course, it's possible using a technique called marshalling. Basically, when the some memory allocated on the host, when a function that allocates memory on the host, it is allocated on the host, and then the memory address is translated using a table on the guest side. For example, in this case, we create a new we create a new function. We push the pointer of the new function to the host. We use a way to use the name of the function in order to select the actual function that have to be executed on the host. On the host is executed the function, and then the result is sent back to the guest device. Of course, it's not possible to use directly memcopy in this case, because the memory allocated on the host could be managed on the guest side only using the function made to manage the memory. And this is an example how a CUDA function is invoked. If you are familiar with CUDA programs, the first thing that have to be done with CUDA is initialize the context, and in this case we want to get the number of a CUDA device. Of course, intentionally the code of the main program is simplified. We have to run the function of CUDA get device count. The function of a CUDA device count belongs to the SD key. The only one argument is the pointer of an integer. This integer will be filled by the SD key with the number of the device available. Now, in the CUDA lingo, in the CUDA language, we have the name host has the machine that hold the physical GPU, and we call device the device, because imagine the GPU is a coprocessor. That means it's seen as a different device on the host machine. Here in the GVirtuos we have a problem with names, because we deal with virtualization. In virtualization we have the word guest to refer to the virtual machine or the remote machine, and host as the machine that hosts the virtual machine. In this case, we have to fill the number of GPUs passing a host pointer that actually is a guest pointer. That means we need some translation, and that means that our front end have to, first of all, get the reference to the front end. As you can see, the implementation of the CUDA get device appear to be real one, the regular one, but it isn't. The implementation is a method and signature appear to be the same, but the implementation is different. We get the pointer to the front end. We have to add the last pointer is basically the parameter. Then we execute physically the CUDA get device count. At this point, there is the interaction with the communicator and is invoked on the backend. The function handle get handle CUDA get device count. We get back the input buffer, basically where the pointer has to be set. We execute the real get CUDA get device count. Then finally we prepare a buffer to send back to the guest device, the guest machine, the result. These are exactly the same, but with the OpenCL function. As you can see, the approach is exactly the same. It's split driver, the plugin works in the same way. It changes, of course, the signature, but even the two programming models are pretty similar. For GPGPU is basically the same. We have just to enable or not the OpenCL plugin. And the next thing is you can share the same physical device on different backend, different front ends, even using different virtualization libraries, for example, CUDA and OpenCL at the same time. One short word about the communicator. The communicator is a really critical component. The most part of the lack of performance in computation is due to the communicator. We have different communicators. The Unix socket is used just for testing purpose. It's used to check if the virtualization works, not to check real virtualization for because the limitation in Unix sockets. The TCP communication is mainly the most used in the most part of installations of GPGPU because there are some. It was born for testing purposes. It was born to test the communicator, but then it was used for remote and distributed virtualization in cloud, and even in the high-performance Internet of Things, because in this way we can invoke GPGPUs or better CUDA kernels using GPGPUs even by a Raspberry Pi. There are other libraries with a really high performance in communication. For example, XenLoop. XenLoop is used for Xen. It is an interface between physical machine and a virtual machine, a high performance interface based on shared memory. And VMCI is exactly the same for VMware. And finally in VM channel is used by KVM. That means it depends by which kind of application of GPGPU I want to run, which kind of GPU as a service I want to set up, and I have to choose the communicator. But how it works, we know. How much it works, I will show you now. Basically, these benchmarks have been used. Have been done with different configuration. This first one is about a cluster made by three TK1 ARM-based computing nodes that have on board their own CUDA device, but it's a really simple CUDA device. And but this cluster is accelerated by two NVIDIA Titan device on an x86-64 machine. On the left of the slide, the architecture of the cluster. On the right, in the center, the computation approach of MPI and CUDA matrix-matrix multiplication. It is a really common pattern in high-performance computing and high-performance cloud computing. So it's a benchmark that could validate the implementation. And we have the same test with one computing node, two computing nodes, and three computing nodes, using GVirtuos and not using GVirtuos. When we use GVirtuos, when we don't use GVirtuos, we use the local CUDA device. When we use GVirtuos, we use the remote CUDA device. As you can see, the improvement of performance is remarkable. Now, let's consider another scenario. This is not a test. This is a real application. This is a real application about interpolation of geographical data. We use an IDVU algorithm. This is actually a really important application for GIS, weather, climate, geology, and with the basically with the availability of big data in earth science, the most part of model coupling is a problem of interpolation. Interpolation of really big data. And doing this with GPU is the only way to manage this. Otherwise, the computing time is really impracticable. And we use this benchmark of interpolation in many configurations. This first configuration is using two local machines. One is called Saturn, where we have a couple of GTX, Titanx, NVIDIA device. And on Saturn is set the backend, then a dedicated 1 gigabit Ethernet, and then another machine called the Storm. Storm actually is this machine where GVirtuos was born. Storm is provided by a couple of NVIDIA Tesla 1060 CUDA device, basically too old to be used for the today requirements. Basically, even the software is not able to work, or is able to work with a really poor performance. As you can see, we have the on the horizontal axis, we have the number of known points in interpolation, while on the vertical axis, the computing time. The scale, of course, is not linear. As you can see, in using remote GPU, we have a really important improvement in scalability. Basically, we increase the number of known points, and we have a really poor increment of the time needed to computation. Let's consider another setup. In this case, we use Amazon Cloud. We use Amazon Cloud setup, We use Saturn as backend. That means the physical GPU is outside the cloud. And while we want to use free micro instance Amazon Web Service virtual machine with, of course, no GPU to do GPU computing. And that's incredible. It works, first of all, and even the results are very good. Even considering the need to remove the competition from Amazon Web Services to our physical machine in the lab. Now we consider cloud to cloud. This is a really interesting setup because we have the backend on an Amazon Web Service machine and the front end on the Amazon Web Service machine in the same zone, of course. And even in this case, the improvement in computation is remarkable. Now we have another setup. In this case, we have on the same on Saturn, on the same physical machine, 1 kVM virtual machine, and we execute the same test. Even in this case, we have a good improvement. Then we have two virtual machines. Of course, the performance with the two virtual machines are decreased, but in any case, still more convenient than not using computation as a service. GPU computation as a service. Now, in the introduction, I mentioned there is a mobile cloud computing application about GPU virtualization and above all GPU computing as a service. Just analyzing the Android architecture, we can understand why Android was so successful. Basically, there is a completely decoupling between the underlying Linux kernel and libraries like the WebKit, Media Framework, SSL are not reported here, for example, SQLite, whatever, and the application framework and the application that are written mainly in Java. The magic is done, or better in this case, was done by the, or better, is done by the Android the runtime with the different version of the Android runtime. The just-in-time compiling was substituted by compiling at the installation, but basically the approach is exactly the same. This is very good because the abstraction, but there is a lack of performance, of course. We cannot compare an iOS-based application and an Android application on the same hardware, But the Android application to work even better needs more hardware resources. Is CUDA used in Android? Actually, with the idea of the Android is down level of features, of course. Or all Android devices support CUDA, or only few Android devices support CUDA, or better, or no one Android device support CUDA. And actually, the NVIDIA Shield tablet and console game console use Android and CUDA. They have their own implementation. Of course, this is done adding a CUDA library in the library section, and it works on proprietary hardware, and of course it's open source. So theoretically, it's not possible to execute CUDA kernels in Android. Nevertheless, yes. Basically, just extending the split driver model I already showed you. There is a component called GVirtus for Java that actually is GVirtus for Android. It's Java independent. It works even with Kotlin. And basically, the idea is, in this case, we have a different, we have a framework based on JNI that basically imitates the behavior of the regular front-end Linux. In this way, we have exactly the same backend for both Linux, theoretically Windows, and even Android applications. The architecture is almost the same. In this case, we have to manage the device code in the right way. We have to store kernels in Android. This is possible using binary large object, and then we can move the compiled CUDA kernel or the fully compiled or partially compiled CUDA kernel on the Android application. In this case, once the Android application is enabled for cloud for GPU computation on the cloud, the use of GPU computation on the cloud is completely transparent. And even for this is really good for the developer, because if you have some let's say machine learning task, and you have you need for GPGPU computing for this task. If you want to deploy an application, a mobile application, you have to deploy the mobile application, the remote API, and a server backend with the GPU. While in this case, you have not to deal about the server backend, you have just to deal and focus on your application. You have to test your kernels, your x86, 64 physical machine, and then deploy the CUDA kernel on the mobile application. Is it running or not? Because the point is, it works or not? And if it works, how it works? Of course it works. This is an application that was made exactly to test this in Android, and this application was used on different Android device in order to show that it's completely transparent for Android. We have the usual approach to test GVirtus behavior using the matrix multiplication. In this case, is really similar to the one used in the first benchmark, but of course doesn't use MPI. This is the code, the original code on the left, the original code of matrix multiply multiplication, matrix multiply in C from the NVIDIA SDK. And on the right is exactly the same code, but using the Java SDK developed for GVirtus. In this case, the virtualization, of course, is not transparent. In this case, you have to use a programming model to use the GPU on Android device. And this is what happens. You are running this application on different device. Usually in green, there's the results using GPU virtualization, and in blue, the results in using not using the virtualization. On the we tested on a tablet using a ZenPad 8. with a Qualcomm CPU. We used on Pine 64 is really similar to a Raspberry Pi, just with more computing power. Actually, this is related to Raspberry Pi up to the number 3, not the number 4. We have to test with number 4. And then the same with other machines. Maybe the most interesting is the Udinio. It's a really small ARM and Arduino device, and it's interesting because it's possible to implement. It's the demonstration that this works in Internet of Things environment. In this slide, actual results. It's incredible because in this slide we show the results of computation even using just the regular connection. There is not one improvement or whatever. Of course, for problem of small sites, the local computation wins. This happens, but when the computation is more demanding, the option of demanding offloading the code on the cloud, it's winning. This slide shows the results with 3G connectivity. And if I remember, these results were made using 3G connectivity while I was in Salt Lake City and the server was at the University of Napoli, Parthenope. So, finally, why GPGPU, virtualization, and mainly remoting? Because we can embed GPU virtualization in the Internet of Things. And on tiny hardware, we could have in the future GPUs, but in any case, the GPUs on the high-end GPUs are more powerful. And for example, some biosurveillance applications, for example, this company used Virtus because it was the partner of one of the partners in the H2020 Rapid project. They are using Virtus in order to perform the computing directly on the surveillance camera and move just the feature, not moving the images, even a huge improvement in terms of privacy. And of course on mobile devices, because in this way we can improve mobile developers to GPGPUs, and especially in a scenario of edge computing where a part of the computation of a mobile device is offloaded not in the cloud but on the edge between the cloud and the connection provider infrastructure. Of course, this is not a recipe good for food. It depends. There are some applications that could be greatly improved if remoted, and other application that is just not usable to remote. Typically, application for rendering, for example, for now it's better having on board, but in the future we don't know. Then the GPGPU kernel is embedded in the app. You have not to set up a web service in Influx or nothing. Virtus is still under development. It's continuously developed. Now we are developing other kind of communication. Recently, we released the CUDNN for deep neural network applications, but still to implement QSparse, for example, in order to have TensorFlow working in Virtus on the cloud. Tinker is a tool for CPU offloading. That means not GPU offloading, but CPU offloading. And the Tinker and GVirtus were integrated in the Rapid project. This was something we did, and probably we will improve in the future. So there are some reference. Of course, if you interest is in GPU computer, it's good to cite these sources.